Okay, let's get started with today's class. Good evening. I'm Shankar. Uh, I'll be your teaching assistant for today's live session on fluid and particles mechanics course. Now, this is the 12th week of the live lectures. This course is offered on NPTEL by Professor Smestampi and Professor Basavaraj. And let's get started with the questions that were given as problems for week 11 on this course. Let's get started with the questions now. Yeah, okay. So first, consider an elbow joint that is shown in figure here. A liquid of density 790 kilogram per meter cube, velocity 200 millipascal, is flowing through the duct at a rate of 0.05 meter cube per minute. So what we have here is an elbow duct shown here, and there is some fluid that is flowing through this elbow duct. And the average velocity at the inlet at section 1 is asked. Now the average velocity, as we have been doing so far, is very straightforward to calculate. All you have to do is V bar is in whatever regime it is there, the average velocity is basically the flow rate divided by the area. The area pi into let's say let's use the same notation as given, pi into d1 square by 4. Here the flow rate q is 0.05 meter cube per second. The diameter d1 is 10 centimeter, which is 0.1 meter. Therefore, the average velocity at the inlet is very straightforward now, 0.05 divided by pi times 0.1 square by 4. Now, I'll give you a minute to finish off the calculations to give me the exact number. Okay, the answer will come to 6.36 meters per second. It's very straightforward. We have been doing these kind of questions for quite some time now, so then don't think there should be any confusion here. We'll move on to the next question, where the average velocity at the outlet is asked. So that again is the outlet velocity is again q by pi d2 square by 4, and it is given that d2 is equal to 6 centimeters, which is 0.06 meters. So for the outlet velocity is 0.05 divided by pi times 0.06 square by 4. Okay, the answer is 17.68 meters per second. Again, very simple calculations. Now we'll move on to the calculation for Reynolds number at the inlet, which is rho times Vi times d1 by mu. And in the question, it is given that the density of the fluid is 790 kilograms per meter cube, the viscosity is 200 millipascal a second, which is 0.2 in SI units, which is kilograms per meter second or pascal second, just pascal second. Substituting these values, we'll get 719 kilograms per meter cube times Vi. If we remember, it was 6.36 meters per second. So it is 6.36 meters per second times d1, that is 10 centimeter, which is 0.1 meter, divided by the viscosity, which is 0.2 kilograms per meter second. Now these are all fairly straightforward calculations. I'll wait for a minute for you to complete and find out the answer here. Okay, the answer is 2512 is what I got. I am hoping that you would also get the same answer here. Similarly, you have to find the Reynolds number at the outlet. Only values that are changing are the velocities and the diameter. The density and viscosity are the same. I'll give you a minute to finish off the calculations here as well. Okay, the answer will be 4190 approximately. Although the answer given in the website, on the SWIM website, is around 8000. I think I don't know where the answer came from, but according to my calculations, I have gotten a value of 4190, and that seems to be fairly accurate here. Okay, we'll move on to the next question. Now, here we have to assume that the flow is laminar at the entrance and turbulent at the exit of the duct. We can write the velocity profiles for V1 and V2 like this. We have to find out what the momentum correction factor at the inlet is. And how do we find that out? As per the discussion we have had in class, let me take a new page here. Yeah. Right now, what is the momentum correction factor? Beta is given by 1 by a integral of u by v bar the whole square dA. Now there's a small mistake in the question. I don't know if you have realized it, but I'm hoping that you would be able to catch something like this on your own. It is given that the flow is laminar at the entrance, and it is the V1 is related to the average velocity as V1 equal to V average times 1 minus R square by R1 square. Apparently, that relation will be incorrect over here, because you know that the instantaneous or the velocity in the x direction will be equal to the max velocity times 1 minus r square by r1 square. If you are considering r1 over there, only then will this equation be satisfied. So that was a mistake that's been given in the SWAYAM website or in the NPTEL. Therefore, if you do this and if you write we know that for laminar flow, we know how the maximum velocity is related to the average velocity, where it is given that u average is basically twice the maximum velocity. So if you substitute this here and substitute for area as pi r square, let me write that as pi times r1 square times integral from 0 to r1 u by so from these two relations we can get that u is equal to uh, u average by 2 1 minus r square by r1 square. Therefore u by u average will be equal to 1 by 2 times 1 minus r square by r1 square. Substituting this here, we'll get that as 1 by 2 times 1 minus r square by r1 square, the whole square times dA. So dA is the differential area, which is basically d of 2 pi, differential of pi times r square. Here r is any radial location along the duct. This means that we can write this as 2 pi r dr. dA is equal to 2 pi r dr. So if we substitute for dA as 2 pi r dr, we just need to rearrange it a little bit and find out the value over here. So we can write that as 1 by r1 square integral 0 to r1, or yeah, so these, okay, let me see now. This pi gets cancelled, 2 becomes 2 square because there's a square here, and there's a 2 here which gets cancelled, so there will be a 2 on the denominator here, times we just have to integrate 1 minus r square the whole square times r. So r times 1 minus r square by r1 square the whole square dr. We need to integrate this now. Therefore, before we integrate, let me expand what is written in that. So the outside the integral remains the same, 0 to r1 remains the same. Let me write this as 1 minus 2 r square by r square plus r raised to 4 by r1 power 4 dr. Again, I can still simplify it. Yeah, there we go. Yeah, again I can simplify it. I can take r and multiply it inside, and then we'll be able to get 1 by 2 r1 square integral 0 to r1 r minus, you have to multiply r with everything in the bracket, so it is r minus 2r cube by r1 square plus r times r power 4 by r1 power 4 will be r power 5 by r1 power 4 dr. Integrating, will be getting 1 by 2 times r1 square times r square by 2 minus r raised to 4 by 2 r1 square. Please let me know if you are able to follow, plus r power 6 by 6 r1 power 4 within the limit of 0 to r1. So what I did here is very simple. R power 3 integral will be r power 4 by 4, and that 4 will cancel with this 2 and give you this 2 over here. Okay, so we'll get 1 by 2 times r1 square times r1 square by 2 minus r1 square by 2 plus r1 power r1 square by 6. If we substitute the upper limit, we'll get r square by 2. r1 square, r1 power 4 by 2 will be r1 square by 2. r1 power 6 by r1 power 4 by 6 will be r1 power 2 by 6, or r1 squared by 6. Therefore, oh, so sorry, wait 1 second, I think I made a mistake somewhere. Let me just figure out what I have done wrong. There is some small mistake I am trying to figure it. Hmm. Not able to figure out, somewhere I made a simple calculation mistake. But if you do this integration directly in the calculator, just substitute for these values. R into 1 minus r square by r square by r1 square the whole square, which is a square minus 2ab plus b square. Okay. And if I substitute, multiply with r cube r raised to 5. And if I integrate that, r square by 2 r raised to 4 by 4 and r raised to 6 by 4, limit of 0 to r1 square by 2 minus r1 power 4 by 2. You'll get the final answer as square by 2. Okay, r1 square will get cancelled, just 1 by 12. Shouldn't be. I'm not able to figure out where I have made a mistake with the integration. There seems to be some error, but you'll get the final answer as 1.33, which is the beta value for laminar flows. All you need to do is plug in this whole equation into the calculator and you'll be able to get the answer. Okay, I'm able to get the answer when I plug it into the calculator. I am not sure why I am not able to get an answer here. A square minus a minus b the whole square is a square minus 2ab plus b square. Okay, I'm a little bit disappointed, but it's alright. Now, what we have to find out is the okay, let's move on to the next question. I think I'm giving up over there. We have to find out the momentum correction factor at the outlet, and again, this is again wrong, which is given as which is this part would again be u max. So u2 would be equal to u max times 1 minus r by r2 the whole power 1 by 6, and you can find u average, or how it is denoted, v bar 2 should be equal to, you have to find the area here, 1 by a integral of u2 dA, which is 1 by pi r1 square, integral from 0, sorry, this is r2, 0 to r2 into 1 minus r by r2 power 1 by 6 times r times, or sorry, again dA has to be substituted for the differential area, which is 2 pi r dr, and again we can cancel out some of the terms here, which is yeah, 1 by r2 square integral 0 to, this would be a little bit different, this should be 2 by r2 square integral 0 to r2 1 minus r by r2 the whole power 1 by 6 times dr. Now the reason we are doing this is to find a relation between u bar and u max. So we can substitute for u max here. First we find out what the relation, what the value of v2 bar is. So ultimately what we'll find here is V2 bar as a function of R2, and from here we get a relation for V2 bar and V max. Now all we have to do is substitute for the average velocity V2 bar in the presence of V2 max, and then integrate for to get the kinetic energy momentum correction factor. So again we'll do some part of it, but I'm expecting you guys would be able to solve. It would be 1 by a integral of 0 to r2. I'll just write what a is. It'll be pi times r2 square 0 to r2, 1 minus r by r2 power 2 by 6 times r times, sorry, again we have to substitute for the differential area, which shall be 2 pi r dr. I'll give you guys a minute, see if you are able to understand it. If you have any doubts, please feel free to ask. I'll give the answer in a minute so that you guys will be able to solve this answer. Okay, finally the answer will come to 1.027. So this is fairly complex. It takes a lot of time to integrate, find the relation between the average velocity and maximum velocity, and then substitute that in the equation for beta and then solve. So this is very time consuming. I'll be giving you the answer as yes, but please try to solve it and let me know if you have any doubts. Okay. Now, next question is, neglecting any pressure and viscous effects, compute the force acting on the duct due to the momentum exchange alone. So, momentum exchange, the force due to momentum exchange in the x direction basically means that we have to consider in this direction. So, there is a force that's acting here, there is a force that's acting in this direction, and that would be given by F times. We just have to find out the vector of the we have to split this vector into a cosine and the sine component, and the cosine component would be giving you the summation of the cosine component, and this vector will give you the fx, and the fy will be given by the sine component. So let me write that down and please let me know if that makes sense to you. So fx is basically when given by the correction factor at the outlet times the mass flow rate at the outlet times the velocity at the outlet minus beta 1 times mass flow rate at the inlet times velocity at the inlet. Now, in order to write this in terms we have found out, we'll be writing this as density times area times velocity minus here as well it is density times area times velocity. So we can write this as beta rho a2 v2 square minus beta 1 rho a1 v1 square. Oh, so sorry. There is cos theta associated with this because this is the cosine component of the force that we are dealing with here. Okay, so here as well it will be beta 2 rho a2 v2 square times cos theta minus beta 1 rho a1 v1 square. Now we found the beta 2 to be 1.027 times 790 times area is pi by 4 into 0.06 square times v2 square would be 17.68 square times cos 30, which is I think it will be root 3 by 2 minus 1.33 times 790 times a1. A1 is pi by 4 times 0.1 square times 6.36 square. Okay, you will get this answer to be somewhere around 280 Newton. Yeah. All right. Sorry for the long interval. Let's move on to the next question where we have to find out the force in the y direction. So if y is basically the sine component of this part alone, and this does not contribute to any force in the y direction. So if you take a look at that, it will be B2 times A2 times rho V2 square sine theta, which is basically, I just quickly written down what is B2 into M2 dot times V2 times sine theta. And if we substitute the values, we'll be getting 1.027 times pi by 4 times 0.03 square, sorry, 0.6 square times 790 times sine 30. So I'll give you a minute to quickly calculate. No, I almost forgot to add the V2 square, which is times 17.68 square. Okay, I'll just give you the value directly. It will be equal to 358 Newton. Okay, let's move on now. In the previous calculation, you would have used the momentum correction factors as shown here and here. So we have to neglect the momentum correction factors and calculate the value of fx, which is basically m2 v2 minus m1 v1. So this would come out to be rho a2 v2 square minus rho a1 v1 square. Sorry, again here I keep forgetting to add that cosine 30. Yeah. So it would be same calculations that would be done there. Yes, we'll get this value to be 353.6. Just keep this 0.7 Newton. Similarly, we just have to calculate it in the y direction as well, which is m2 u2 sine 30, which is rho a2 u2 square sine 30, which is 790 times pi by 4 times 0.06 square times 6.36 square times sine 30. Oh, so sorry, there is a small mistake. This is not 6.36, this is 17.68. Yeah, finally, this value would be 349 newtons. Okay, let's move on to the next question where we have to calculate the kinetic energy correction factor at the inlet. which is given by alpha is equal to 1 by a integral 0 or integral u by v bar the whole cube dA. Again, if you calculate it for laminar flow, it will be 1 by pi r1 square integral from 0 to r1 u by v bar, as we discussed earlier, was not this but this sorry, excuse me, yeah, the relation between u by u bar is half into 1 minus r square by r1 square. So let's substitute that here. Oh, it would be 1 by sorry, it would be 1 minus r square by r1 square cubed times 2 pi r dr, substituting for the differential area. Now we'll do a little bit of manipulation. As we have seen earlier, it will be, sorry, there is a half that's coming up as well. So it would be 1 by 4 times r1 square integral 0 to r1 1 minus r square by r1 square the whole cube r dr. Okay, yeah, so that would be let us expand the cubic term now. It would be 1 by 4 r1 square into integral 0 to r1 into r times 1 minus 3 r square by r1 square plus 3 r power 4 by r1 power 4 minus r power 6 by r1 power 6 dr. It should be 1 by 4 r1 square integral 0 to r minus 3r cube by r1 square plus 3r power 5 by r1 power 5 minus r power 7 by r1 power, oh, so sorry about that, it is power 4 power 6 dr. And integrating, we'll get 1 by 4 r1 square times, I just have to substitute for the upper limit after integration, so it is r1 square by 2 minus 3 r1, sorry, r1 square by 4 plus 3 r1 square by 6 minus r1 square by 8. Well, I don't know. Again, I think I'm making some kind of mistake somewhere. I don't know what I'm doing wrong. The final answer would come to 2. Similarly, we can, as we have discussed for the momentum correction factor, we have to derive a relation between u bar and u max as follows. Then substitute for u bar here, and you have to substitute for u bar as 1 by a integral 0 to r2 u bar by u max, sorry, u by u bar the whole cube dA. And if you perform the substitution correctly, you'll get an answer of 1.077. Okay. Now it is given that the pressure difference between pressure head loss is 10 meter and the frictional head loss is 1 meter. The height difference between 1 and 2 is what is asked. So let's first consider the kinetic energy correction factor and write down the equation as P1 minus P2 by rho G plus Z1 minus Z2 should be equal to the HF plus V alpha into V2 square by 2G minus alpha 2 V2 square and alpha 1 V1 square by 2G. All the values are given, we just have to find out the value of Z2 minus Z1 because that is Z2 is supposedly higher than Z1. P1 minus P2 by rho G is minus 10. HF is 1 plus 1 point, alpha 2 is 1.077 times V2 square is 17.68 square by 2 times 9.81 minus 2 times 6.36 square by 2 into 9.81. Okay, I got this answer to be somewhere around 4.03 meter. I'm not sure whether that matches with what is given in the website. Okay, now we just have to neglect the kinetic energy correction factors and perform the calculation once again. We'll get this answer to be 4.87 meters. Okay, let's move on to the second set of questions, which deals with this. Consider a pipe shown in figure. This is a galvanized iron pipe system and delivers gasoline at 20 degrees Celsius at a flow rate of 0.036 meter cube per second. If the pump is running and there's a pump here and this is one of the parallel pipes and delivering 45 kilowatts to the flow in pipe 2, then determine the following. For gasoline, you may take the density to be 680 kilogram per meter cube and viscosity to be 2.92 into 10 raised to minus 4 kilogram per meter second. First, we have to find the galvanized iron, the roughness height of galvanized iron, and here in this is done by going to the Frank White's fluid mechanics book. So this is basically going through this obtained by going through this fluid mechanics by Frank M. White and in the, by of I think it's McGraw-Hill Publications. Yes, it is McGraw-Hill Publication. In the 7th edition, in page 381, you will be able to see the roughness height of galvanized iron in millimeter, which is 0.15 mm. Alright, we need to find the roughness ratio at the inlet. We have to assume that this is the inlet over here and the pipe is the outlet over here. So the pump delivers to the outlet over here. So therefore the roughness ratio at the inlet will be equal to 0.15 by 50 millimeters which will be equal to 0.003. This is both in mm. Then we have to find out the roughness ratio. Let me mark this as Ki. We have to find the roughness ratio at the outlet, which is given by 0.15 by taking out this value, which is 40 in millimeters. This is equal to 0.00375. Now what we need to do is solve a set of equations to find out the velocity, the Reynolds number, the friction factor, the volumetric flow rate. These four parameters have to be calculated by simultaneously solving two equations. One which contains the total flow rate, which is Q as Q1 plus Q2, and second one being relating the head loss in each of them. Let's try to solve them right now. I'll just give you how and tell you how to solve them. So first we have to write down the equation for the equation for velocity. The volumetric flow rate. Q is equal to Q1 plus Q2, and it is given that the exit flow rate Q is 0.036, and we can equate that to this. Now we have an equation for velocity here, which is given as pi by 4 times v1 pi by 4 b1 square times v1 plus pi by 4 b2 square times v2 equal to 0.036. Right, now we need to take one more equation, which is the pressure balance equation across these two ends. You know that the head will be matching here. H1, if this is H1, the head loss over there, then that should match with H2 minus the head loss offered by the pump. So H1 should be equal to H2 minus H pump. How do we find out each of them? H1 is basically the equation for the F friction factor, which is F1 times L1 by D times V1 square by 2G, should be equal to F2 times L2 by D, again D1 D2 comes into the picture, times V2 square by 2G, and uh, the H pump is given by the power offered by the pump by rho times Q, which is the mass flow rate, times G. Now we have to find out F as a function of velocity. You know that F is a function of velocity, so you have to substitute that again by using the transcendental equations or finding from the Modi's chart. So again I'll write F1 as F1 times L1 by D1 times V1 square by 2G should be equal to F2 into L2 into V2 square by D2 times 2G minus, this is 445 kilowatt, I guess, is the power offered by the pump, which is given here, which is 45,000 watts, divided by 760, or is it, no, sorry, 680, times pi by 4 times the flow rate in the a second leg, which is given by pi by 4 d2 square times v2 times 9.8. Now, the solution of this is extremely difficult. As you can see, the f is a coupled equation in V, and for finding f, we need V. For finding V, we need f. And once we solve this equation, we need to verify it by putting it in this equation. And it needs an iteration mathematical technique to solve it. So I'll give you 5 minutes to see if you can. I'll give you an approximate value for V2. Yeah, can you please find out V1 and please let me know. Try V2 equal to 15 meters per second and 16 meters per second. So I'll give you plenty of time to focus on this, after which I'll explain the answer that. Okay, I'll finish by giving these answers. So please do try it out again if you can find this out for yourself. If we do this, we'll be getting V1 as the first method will get V1 as 8.73 meters per second and this as 8.09 meters per second. So there is a particular V1 and V2 which corresponds to a value in between this, which is given by V2 is equal to 15 point, sorry about that, it is somewhere between 15 and 16. So if V2 is 15.39, V1 would be 8.48. This is in meter per second. This is in meter per second. Similarly, Reynolds number at inlet would be equal to, sorry, at 1 will be equal to 1.43 into 10 power 6. And at position place 2 will be equal to 9.94 into 10 power 5. And the friction factors will be equal to 0.028 and F2 would be equal to 0.0263. Finally, the flow rates will be equal to 0.0193 and Q1 would be equal to 0.0167 meter cube per second. Okay, with this, I think we'll stop. I know I'm not done the, all they have asked is the volumetric flow rate, etc. And the pressure drop is basically delta P will be the same for both, which is F times L1 square by D1 times V1 square by 2G. And here it will be delta P is equal to FL2 by D2 V2 square by 2G minus the H pump which was described earlier, and both of them will be equal to 774 kilopascal. Because it is conducted in parallel, the pressure drop will be the same. Now the week 11 practice problems I am not going to solve now because of the lack of time. And with this, I think I'll stop for today's lecture. I sincerely thank you for your time and attention. Please feel free to ask any questions. I'll be happy to answer you. Thank you.